An earthquake is a natural occurrence. Like rain, earthquakes affect almost every part of the earth, and like rain, they can be either mild or catastrophic. Over the course of geological time, earthquakes, floods, and other natural events have helped to shape the surface of our planet. An earthquake may last only a few seconds, but the processes that cause earthquakes have operated within the earth for millions and millions of years. Until very recently, the cause of earthquake was unsolved mystery. It was the subject of fanciful folklore and equally fanciful learned speculation by peoples throughout the world. An earthquake is a sudden rapid shaking of the earth caused by the release of energy stored in rocks. This is a brief definition which students of all ages can master. A full definition of the term, however, would need to include a good deal more information. Students may be surprised that we speak of rock layers because in many places the rock material of the earth crust is covered by accumulations of sand or soil. Remind them that even beneath the sediment in river valleys, plains and beach areas, some kind of rock is always present. Earthquake refers to the result of a sudden release of energy in the earth's crust that creates seismic waves. It may also refer to sudden and violent shaking of the ground, sometimes causing great destruction. The point where the rocks actually break is the earthquake focus. Large subduction zone earthquakes can break along a fault for hundreds of kilometers. The epicenter of these earthquakes is directly above where the earthquake actually started along the fault line. The amount of destruction at the epicenter of an earthquake is directly affected by its size and the depth where the rocks rupture. The epicenter of an earthquake is the same whether the rocks ruptured at 50 kilometers, 100 kilometers or even 300 kilometers beneath the earth's surface. Studying epicenters, seismologists use seismographs to study the earthquake epicenter. Using these epicenters, they can discover the location of unknown faults and crustal plate boundaries. Scientists are especially concerned about epicenters of past large earthquakes in cities like Tokyo in Japan and Los Angeles, California in United States of America. Both of these cities are located in major fault zones. Next aspect is the focus of an earthquake. Earthquakes with a focus of less than 70 kilometers are the most destructive. Therefore, when listening to earthquake reports, it is important to know the geographic location of the earthquake listed as the epicenter and the depth of the earthquake. How to locate an earthquake's epicenter? The epicenter of an earthquake is the area on the surface directly above the focus of an earthquake. By locating the epicenter, seismologists can determine where in the earth's surface the earthquake waves originate from. This will help predicting and preparing for future quakes and hazards. To locate the earthquake's epicenter, you need a seismogram from 3 separate seismic stations. Study the seismographs and find the elapsed time between the arrival of the first P wave and the first S wave. By determining the SP time and using a time distance graph, you can find the distance to the epicenter from the seismic station. Now, on a map, draw a circle around the epicenter, in which the radius of the circle equals the distance to the epicenter. Draw circles around the other 2 seismic stations. The point at which the three circles meet is the epicenter. In an effort to get accurate earthquake readings, the United States has created a worldwide network of over 100 seismic stations operated through Golden, Colorado. The largest station, located in Billings, Montana, has 525 instruments grouped in 21 clusters covering a region of 200 kilometers in diameter. By using information from the instruments in Billings, seismologists using high-speed computers are able to locate an epicenter by a trial and error procedure. Scientists use a method called triangulation to determine exactly where the earthquake was. It is called triangulation because a triangle has three sides and it takes three seismographs to locate an earthquake. If you draw a circle on a map around the three different seismographs, where the radius of each is the distance from that station to the earthquake, the intersection of those three circles is the epicenter. Earthquakes are of three types. They are shallow foci earthquakes, intermediate foci earthquakes, and deep foci earthquakes. Most parts of the world experience at least occasional shallow earthquakes, those that originate within 60 kilometers or 40 miles of the Earth's outer surface. In fact, the great majority of earthquake foci are shallow. It should be noted, however, that the geographic distribution of smaller earthquakes is less completely determined than more severe earthquakes, partly because the availability of relevant data is dependent on the distribution of observatories. Of the total energy released in earthquakes, 12% comes from intermediate earthquakes, that is, quakes within a focal depth ranging from about 60 to 300 kilometers. About 3% of total energy comes from deeper earthquakes. The frequency of occurrence falls off rapidly with increasing focal depth in the intermediate range. Below intermediate depth, the distribution is fairly uniform until the greatest focal depths of about 700 kilometers or 430 miles are approached. The deeper focus earthquakes commonly occur in patterns called Benioff zones that dip into the earth, indicating the presence of a subducting slab. Dip angles of these slabs average about 45 degrees, with some shallower and others nearly vertical. Benioff zones coincide with the tectonically active island arcs such as Japan, Vanuatu, Tonga, and the Aleutians, and they are normally but not always associated with deep ocean trenches such as those along the South American Andes. Exceptions to this rule include Romania and the Hindu Kush mountain system. In most Benioff zones, intermediate and deep earthquake foci lie in a narrow layer, although recent precise hypocentral locations in Japan and elsewhere show two distinct parallel bands of foci 20 km apart. The first one among these effects of earthquake is the direct shaking hazards and human made structures. Most earthquake related deaths are caused by the collapse of structures, and the construction practices play a tremendous role in the death toll of an earthquake. In southern Italy, in the year 1909, more than 1 lakh people perished in an earthquake that struck the region. Almost half of the people living in the region of Messina were killed due to the easily collapsible structures that dominated the villages of the region. A larger earthquake that struck San Francisco had killed fewer people, about 700, because building construction practices were different type, predominantly wood. Survival rates in the San Francisco earthquake was about 98%, that in the Messina earthquake was between 33% and 45%. Although probably the most important direct shaking effects are not the only hazard associated with earthquakes, other effects such as landslides, liquefaction and tsunamis have also played important part in destruction produced by earthquakes. Geologic effects on shaking. When we discussed earthquake intensity, we discussed some of the basic factors that affect the amplitude and duration of shaking produced by an earthquake, that is earthquake size, distance from fault, site and regional geology, etc. And as you are aware, the shaking caused by seismic waves can cause damage, cause buildings to collapse. The level of damage done to a structure depends on the amplitude and the duration of shaking. The amplitudes are largest close to large earthquakes and the duration generally increases with the size of the earthquake. Larger quakes shake longer because they rupture larger areas. Regional geology can affect the level and duration of shaking, but more important are local site conditions. Although the process can be complicated for strong shaking, generally shaking in soft sediments is larger and longer than when compared with the shaking experienced at a hard rock site. Next effect of earthquake is the landslides and liquefaction. Buildings are not the only thing to fail under stresses of seismic waves. Often unstable regions of hillsides or mountains fail. In addition to the obvious hazard posed by large landslides, even non-lethal slides can cause problems. When they block highways, they can be inconvenient or cause problems for emergency and rescue operations. Occasionally, large slides can be triggered by earthquakes. In 1970, an earthquake off the coast of Peru produced a landslide that began 80 miles away from the earthquake. The slide was large. Witnesses estimated its height at about 30 meters or 100 feet, travelled at more than 100 miles per hour and plowed through the part of one village and annihilated another, killing more than 18,000 people. In some cases, when the surface is underlain by a saturated sand-rich layer of soil, prolonged shaking can cause the expulsion of fluid from the sand layer, resulting in large sand blows that erupt through the overlying strata. The other effect of the earthquakes is the tsunamis. Sometimes dramatic byproduct of certain types of earthquakes are tsunamis. Tsunami is a Japanese term that means harbor wave. Tsunamis are frequently confused with tidal waves, but they have nothing to do with the tides. They are the result of a sudden vertical offset in the ocean floor caused by earthquakes, submarine landslides and volcanic deformation. In 1883, the volcanic eruption of Krakatoa resulted in the collapse of a caldera that initiated a tsunami which killed 36,000 people on nearby islands. On June 25, 1896, an earthquake off the Japanese coast generated a tsunami that hit the shore with wave heights ranging from 10 to 100 feet. As the fishing fleets returned to shore following an overnight trip, they found their villages destroyed and 22,000 people dead. In the last century, more than 50,000 people have died as a result of tsunamis. Tsunami initiation. A sudden offset changes the elevation of the ocean and initiates a water wave that travels outward from the region of seafloor disruption. Tsunamis can travel all the way across the ocean, and large earthquakes in Alaska and Chile have generated waves that caused damage and deaths in regions as far away as California, Hawaii and Japan. Tsunamis are initiated by a sudden displacement of the ocean, commonly caused by vertical deformation of the ocean floor during earthquakes. Other causes such as deformation by landslides and volcanic processes also generate tsunamis. The speed of this wave depends on the ocean depth and is typically about as fast as a commercial passenger jet, about 0.2 kilometers per second or 712 kilometers per hour. This is relatively slow compared to seismic waves. So, we are often alerted to the dangers of the tsunami by the shaking before the wave arrives. The trouble is that the time to react is not very long in regions close to the earthquake that caused the tsunami. In deep water, tsunamis are not large and pose no danger. They are very broad with horizontal wavelengths of hundreds of kilometers and surface heights much smaller, about 1 meter. Tsunamis pose no threat in the deep ocean because they are only a meter or so high in deep water. But as the wave approaches the shore and the water shallows, all the energy that was distributed throughout the ocean depth becomes concentrated in the shallow water and the wave height increases. Typical heights for large tsunamis are on the order of tens of meters, and a few have approached 90 meters, that means about 300 feet. These waves are typically more devastating to the coastal region than the shaking of the earthquake that caused the tsunami. Even the more common tsunamis of about 10 to 20 meters can wipe clean coastal communities. Deadly tsunamis occur about every 1 to 2 years, and they have at times killed thousands of people. In 1992-93, 3 large tsunamis occurred, one in Japan, Indonesia and Nicaragua. All struck at night and devastated the local communities. Earth has 4 major layers: the inner core, outer core, mantle and crust. The crust and top of the mantle make up a thin skin on the surface of our planet. But this skin is not all in one piece. It is made up of many pieces like a puzzle covering the surface of the earth. Not only that, but these puzzle pieces keep slowly moving around, sliding past one another and bumping into each other. We call these puzzle pieces as tectonic plates, and the edges of the plates are called the plate boundaries. The plate boundaries are made up of many faults, and most of the earthquakes around the world occur on these faults. Since the edges of the plates are rough, they get stuck while the rest of the plate keeps moving. Finally, when the plate has moved far enough, the edges unstick on one of the faults and there is an earthquake. While the edges of the faults are stuck together and the rest of the block is moving, the energy that would normally cause the blocks to slide past one another is being stored up. When the force of the moving blocks finally overcomes the friction of the jagged edges of the fault and it unsticks, all that stored up energy is released. The energy radiates outward from the fault in all directions in the form of what are known as seismic waves, like ripples on a pond. The seismic waves shake the earth as they move through it, and when the waves reach earth's surface, they shake the ground and anything on it like our houses and us, will collapse. The short answer is that earthquakes are caused by faulting, a sudden lateral or vertical movement of rock along a rupture surface. The surface of the earth is in continuous slow motion. This is plate tectonics, the motion of immense rigid plates at the surface of the earth in response to flow of rock within the earth. The plates cover the entire surface of the globe. Since they are all moving, they rub against each other in some places, like the San Andreas Fault in California, sink beneath each other in others, like the Peru-Chile Trench along the western border of South America, or spread apart from each other, like the Mid-Atlantic Ridge, or collide with each other, like Indian Plate moving in the northeastern direction and hitting the Tibetan Plate. At such places, the motion is not smooth. The plates are stuck together at the edges, but the rest of each plate is continuing to move. So, the rocks along the edges are distorted, what we call strain. As the motion continues, the strain builds up to the point where the rock cannot withstand any more bending. With a lurch, the rock breaks and the two sides move. An earthquake is the shaking that radiates out from the breaking rock. People have known about earthquakes for thousands of years, of course, but they didn't know what caused them. In particular, people believed that the breaks in the earth's surface, faults which appear after earthquakes, were caused by the earthquakes rather than the cause of them. It was Bunjiro Koto, a geologist in Japan, studying a 60-mile long fault whose two sides shifted about 15 feet in the Great Japanese Earthquake of 1871, who first suggested that earthquakes were caused by faults. Henry Reed, studying the Great San Francisco Earthquake of 1906, took the idea further. He said that an earthquake is the huge amount of energy released when accumulated strain causes a fault to rupture. He explained that rock twisted further and further out of shape by continuing forces over the centuries eventually yields in a wrenching snap as the two sides of the fault slip to a new position to relieve the strain. This is the idea of elastic rebound, which is now central to all studies of fault rupture. Can scientists predict earthquakes? No, and it is unlikely they will ever be able to predict them. Scientists have tried many different ways of predicting earthquakes, but none have been successful. On any particular fault, scientists know there will be another earthquake sometime in the future, but they have no way of telling when it will happen. But scientists can tell the areas which are prone to earthquake with the help of seismic zonation maps. However, with the help of abnormal behavior of the animals prior to an earthquake, such as rats leaving their hideouts, fishes jumping above the surface of water, rabbits hopping aimlessly about, by measuring the large fluctuations of water table that occur before an earthquake, it is possible to predict the earthquake, but not much earlier to disasters. Earthquakes are natural hazards that poses threat to mankind. Understanding of the earthquakes and mitigation is a challenge to mankind. By studying the seismic prone regions, one can prevent the damages to the mankind. Seismic zonation maps helps us to create awareness among the general public about the effects of the earthquake. Prediction of earthquake is a difficult task at present. However, with the advancement of the seismic science in future, hope it may become possible.